Okay, so let's get into a conversation about EXVs or EEVs. Doesn't really matter which way you want to call it. It's everybody has their preference, all right, and that's really what that comes down to. It's kind of like the um, whether or not you want to call it a whether they say TXV or TEV, right? It's the same principle applies there, and I do want to just clarify this right out the gate because this is a point that does sometimes confuse some. So a TEV, a thermostatic expansion valve, is the same thing as a TXV. Now, at one time, TEV was a far more common term, and as the years have progressed, maybe with the help of social media in the industry, however the case, most everybody has transitioned to just using TXV as the standard term that the industry has adopted. So, not a whole lot of people would consider using TEV as the standard term. It's the exact same principle though when it comes to T or EXV versus EEV. This there is a split between a lot of people on to which way you want to call it. I do see a lot of people online and interacting with people through Chiller Academy that will use the EEV term, and that's okay. You're not wrong for using that term. It's just two different ways of saying the same thing. It's electronic expansion valve. Whether we use an X or an E in the middle to describe that, it's up to you. So if that has caused any confusion over time, or if it feels like there's a major difference there, I'm just trying to clarify that there's not. Now, I'm going to take a focus in chiller EXVs today, and EXV is just the term I go with. But EXVs have really done a lot to help take over the market, and they dramatically help improve efficiency and our ability to dial in a system. Now, they can be a little bit more complicated to troubleshoot, but my personal opinion is I don't know that there's a real improvement in reliability, but there is an improvement in it's more plug and play for a lot of technicians. What I mean by that is a lot of technicians, especially on the commercial side, we typically have valves that we have to manually calibrate ourselves. We have to make those adjustments, and while they may come from the factory kind of preset fairly close, depending on your circumstances, they may not be where they need to be for your specific application. And that's for a TXV, right? And so the issue that we've always had with TXV is technicians having a deep enough understanding or having the time to properly calibrate the valve upon install. And that was a major failure point. The other side of that is TXVs typically could only derate themselves down to about 30% of their flow, and they could not completely stop flow to isolate. That was a weakness because part of that calibration process with a TXV is we need to be able to tune that valve to that compressor's staging conditions and whatever our load conditions are. And that can be kind of difficult to do, and it takes a lot of time. So not only do you need to make sure that you don't run too high of a superheat at a fully loaded scale. So when our slide is, or I say our slide, when our compressor is fairly loaded, and we've got a good differential temperature difference across our evaporator, we can't push our superheats too high. At the same time, we have to be very careful because if we only calibrate at fully loaded, when we get to an unloaded state, which is uh, for a lot of sites is a very frequent thing. Like you're going to have load swings and fluctuations, and the time of year has a big impact on this. So when you hit that unloaded state, the valve might run perfect, 8-10 degrees of superheat at the top end. It can't derate properly on the bottom end, and it starts to flood. And at the same time, if you calibrate on for the low end, where you've got a proper superheat down there at minimal load, Once you scale up to a fully loaded state, your superheat loses control, your discharge superheat spikes, you put in a ton of wear and tear on the compressor, and you're probably not able to actually achieve the full capacity of that system because you're not able to feed enough refrigerant. You're starting to starve the evaporator too much. So you've got to, like, when you're calibrating a TXV, you've got this whole process where you have to load and unload and you have to see these different variables, and it's really hard to reproduce some of these things sometimes in the field depending on our time of year and the conditions we have at our disposal. The point to this being EXVs have really solve that problem because it's not a matter of mechanical calibration anymore. We don't have to go through this whole process the way we used to. We have to do a couple of things. We have to make sure that the valve is able to stroke all the way, and we have to make sure that our pressure sensors and our temperature sensors are reading accurately. If we have done that in the control system, so we can't forget about that part. The control system is functioning correctly and it's actually controlling and the valve like it needs to. So as long as these things are okay, once the valve is in operation, it's fine. But it's a far more advanced electrically to control that because now these sensors and all these other components now have to work together properly. Now that's not such a big deal in today's age of controls packages that we have. Like we've really come a long way in dialing this stuff in and making it exceptional. All right. But this is where EXVs have really owned their place in the market and from a chiller perspective have really given us a lot of flexibility. It doesn't matter what load conditions are. These valves can, for the most part, or actually all of them that are I can think of, have the ability to fully close. And while it's not good to use them as like a true stop valve for like pump downs and such, I do recommend having a normal solenoid valve. Technically, they can function like that, and that's a failure that I've had, or even not a failure. It's a procedural issue I've had in my early days, especially, and I see apprentices make this mistake. These valves will typically go to full close, and when they go to full close, they will fully isolate if they're working properly. And if you don't force those valves open whenever you do your recovery, there's times where it can trap refrigerant in there, and you get in and start working on stuff thinking you're good, and either the valve suddenly loses seal and opens a little bit, or you go to take something apart on the still pressurized part of the system thinking it wasn't pressurized, and you get hurt or something very negative happens. So these are things we have to be careful with EXVs, but they have this capability. And so our ability to control flow is far more expansive. We can technically go from 0 to 100%, where with a TXV we could only do say 30 to 100%, give or take, right? Now, the valves you're going to find in a chiller are not going to be the same styles that you're going to see in VRF or mini split or even regular split systems in today's standards. Not saying there won't ever be any crossover, but for the most part, we're talking about valves that are at a very different scale. These smaller valves, and the more popular version of those valves is you have a removable head. With our modern valves, we don't have that. Uh, so here's an example of what a very typical modern valve we would see, or the two different styles. And this doesn't matter if it's Sporlan or Danfoss; they follow the same basic uh, mentality when setting this up. So we have our regular head here. Everything is fully attached together. This is one solid body, and I can show you that here via this. So this is the Danfoss. Yeah, this is a Danfoss style valve, and this is one solid body. All of this is one assembly, one piece, all the way down from the plunger to the tip of the motor. Now, some of these, the newest ones, are using a removable plug here. I say removable as in it's got a plug instead of a hard cable. You cannot take this out. This is not serviceable. This whip is permanently a part of this valve body. So a lot of the newest ones have moved away from this style and have moved towards a interchangeable whip. I think that was an improvement. But these smaller ones you may be used to seeing, they've got little the coils slide over the valve body. And so you've got the valve body and then you can take the coil off and on. So that's one of the big separations you're going to see is we don't have a removable stator. That's what that coil piece is. That is your stator. That is fixed on these styles of valves. Even when they get far smaller than what I've shown you, um, that's going to be a very consistent theme. You're not going to have very many of these valves that are scaled to this size, if ever, that have a removable stator. And even with this particular style, you're not going to, even if this motor has a failure, you're not going to pull this stator off of the valve body. This whole plunger assembly is one piece. Now, these do have the ability to separate the main head. So that's what this assembly here would be called. This is your main head. We do have the ability to separate that head from the body uh, of the valve itself. So this is your main valve body. This is your head assembly. Right here at this seam, this is where they thread into one another, and it is just a threading with a mechanical seal typically. Some of them will have a Teflon seal in here, some of them, but a lot of them that I've seen, it's usually a mechanical seal, meaning that we're taking brass to brass and we're making a seal that way. And this is a machined surface, so where the friction of the two joining here, now that's where you have to get your torque really well, will make this seal. Now, and that's if these are so this would be a straight valve. This would be another style of a straight valve, but this is where this one's more of an angle. This is a direct, uh, non-angle up and down. I think there are actual terms for this. Now, an alternative to these, you could have a 90 degree. So a 90-degree valve instead of a straight would be it comes in this way and then goes out the bottom. It doesn't come out the side like this. So it would be a straight pass through down. It just depends on what the manufacturer needed and what style of valve they needed. And that's if they're using a body like this, or where we're in line on our say our liquid line or something. And you'll see this is very common on a lot of air-cooled applications. A lot of your air-cooleds are going to have a valve style like this, and you could have something that looks similar to this. So we've got two different valves. Actually, the two we were just referencing, this is how they would look in a field application. You've got both of them straight pass-throughs. This one's at a slight angle just by its design. And this is your main valve for the evaporator. This was an economizer valve, and this is used in a few different types of systems. Now, not necessarily the braze plate style, but using the EEVs for just various control. This used to be a TXV on older systems, and this has been upgraded to an EEV style. But just to kind of give you a picture of how they're implemented. Our liquid line is coming in through here. We see our filter dryer going through our economizer, and then we're passing through. But you can see the body. We have a side glass here. This body also has a side glass over on the side. And then we have our motor assembly and our head assembly threaded onto that valve body. Now, when these begin to scale into a much larger size, we can start getting into these valve blocks. These valve blocks are quite literally just that. We have an entire block of, this would be like a cast iron block that's been machined, and our liquid line is coming up here into the side. And essentially, instead of using one massive and extremely expensive EXV, to control the flow here. Instead, we can go with a double stack, and you can stack these valves, and essentially this is ported in such a way to where the liquid is sent into this block and then it's routed through each of these valves internally through internal porting. By doing this, these valves can now share the load. So this could be a hundred. This is actually a 300-ton water cooled chiller we're looking at, and you've got a 150-ton valve here and a 150-ton valve here, just to kind of paint the picture of what these are doing. And so they're both functioning together in order to get our flow through them. Now that also means that these need to be calibrated and able to function simultaneously. In a perfect world, these operate perfectly together and they remain in the same position as they stroke back and forth to control flow. But that's not always the case. Sometimes as these valves begin to fail, one can get out of calibration compared to the other, and then one has to open way up while the other one may be stuck or isn't opening as like it needs to, so the other one has to try to compensate for it, which can then lead to just overall flow issues. And if we start running low levels in our evaporator because of something like that. So just to kind of give you another example of what these could look like and how they can be configured in the field in order to handle the tonnage we need. There's several machines that use a valve block like this. Now, there's other valve technology we can get into as we continue to scale larger. There's still a lot of chillers out there that are using fixed plate or fixed orifice, I should say, evaporators. I'm sorry, metering devices. So with a fixed orifice, which they're using a literal just a steel plate with a bunch of holes punched in it. Now it's not that haphazard. It is specifically engineered to have a certain flow rate and pressure drop across them, but it's still a fixed bore style of device. Those are still used even in very large applications because it's a very consistent technology that they can design variability into. That's a whole nother topic in and of itself. But we also see the use of variable orifice valves. So we've got valves in the market now, something that York heavily uses that is basically a butterfly valve, but it's not a normal butterfly. It's a modified butterfly valve that can be used to have to vary the flow and still create a pressure drop, but do it at a much larger scale. A scale that can be harder to do with an EXV body. So my point is you'll start to see these EXV blocks scale up into larger systems, but there is a breakover point to where you either have to go with a really large valve, which financially may just not make sense, or you have to start splitting these valves up into uh, have a multi head function like this in order to get the same volume and flow. Any questions so far up to this point on these valve bodies?
At what sizes you would see EXV, even stock EXVs, versus when it's begin to be a fixed plate? What type of a machine? Most of EXVs would be as screws, or even some smaller centrifugal chillers. Do they have EXVs?
Yeah, so we do see there are some centrifugals in the market that are using EXVs, and specifically the ones that come to mind the first would be ones utilizing turbo cores. Now that's largely because turbo cores can get a lot smaller in size, but you'll see that there's some like a Smart as an example. They have a turbo core line they came out with, and they put a larger valve in, and one valve was able to handle the whole circuit. Right now, Daikin as another example with their turbo cores, and they're stacking multiple compressors on each chiller sharing the same circuit. On their smaller versions, their WMC series, on their smaller versions, they're using a just a single head. It's a large head. It's in a very large block, so it's not a small one. It is quite large, but they're able to get away with that. So I think they're the WMC, as an example, even with two compressors, can scale down to like 125 tons. And I think they're putting like a 125 or 150-ton valve in there to accomplish that. Now, as that scales larger, the larger WMC series by Daikin has a dual head assembly, just like what we saw with that Train RTHD. So that's what this one here is. This is off of a RTHD screw compressor. So these are single circuit systems that are running a large volume of tonnage. With a lot of your air cooleds, even if it's a 400-ton machine, a lot of your air cooleds, it's multi-circuit. So you also have to think about that. So like even a 400-ton machine, it may be two 200-ton circuits, or it may be four 100-ton circuits. And that's where we get into that's how they're able to continue using a single valve head, and it may be economical to just scale that valve head up. Now, that's to say that they didn't do a multi-stack valve. And actually, I should have got a picture of this. I didn't think about that. One of the things that they'll do is, instead of having a block like this, they will have, it'll be a regular body like this, but there'll be two of them. And you have the exact same issues you could have with a block style. It's just they'll have two of these ran via T's. So your liquid line will come in and it will tee off, and then it'll go through two different sets of valve, or two valve bodies, and then it will tee back together as it enters into the uh, the evaporator. So as it's coming back into the evaporator, they'll tee back together. And this was also done with TXVs. Okay, that theory wasn't started with EXVs. There are older machines that we would have two different TXVs on the same circuit, and they had to be calibrated in the same way. It was a very difficult process. At least that's my opinion. Um, so yes, on some of those larger air cooleds, and we are talking about typically screws when we have to start splitting circuits. That is what they'll do, and instead of putting a large, expensive 100-ton, 150-ton a valve in there, they'll split that between, say, two 50-ton valves or two 60-ton valves. Maybe they'll upsize them just a little bit, and those two valves now need to be synchronized and be able to work together. So that, again, that is part of the complexity when you split two different heads like that, is they have to be able to, or it is best for them to be synchronized in order to get a balanced flow through them. Otherwise, you can start creating load issues. So yeah, those larger blocks, you're probably looking at a single circuit water cooled style system. As we move into air cooled side, and it gets split up between multi circuits, I haven't seen one of those EXV blocks, those housings, on an air cooled. But when I do see them split, they'll do the T thing where they'll just tee off the liquid line, go through two valves, and then tee back together on the other side. It is important that the lengths of all these things are very close to one another. Like they in order to get proper flow and keep everything balanced and even, and one valve doesn't get favored more than the other, our links and our turns need to be on point. Otherwise, you can create different eddy currents that make the fluid move in ways we don't want it to. Um, yeah. Now, EXVs are implemented across everything below that too. So even a lot of the older machines that are on the market, while some of them may still have TXVs, a lot of them got converted, and we did a lot of conversions on them to EXV bodies, especially when we had systems that started having routine compressor failures due to flooding, and we had issues getting the valves to tune the way we needed it to. It became a pretty easy upsell to, hey, the manufacturer makes an EXV package for this. Let's just put this in. Like we install this, we put some sensors in here. Now we've got way more precise control over our superheat, and we can better protect your compressors in that process. And it did just that. Like it simplified the process. Yeah, now we got a controller and such in the way, but um, my point being, even with a lot of your older machines, many of them may not have shipped with EXVs from the factory. And it may be a retrofit package that we did at a later point because of whatever reasons. Um, but yeah, all the way down to your smallest scrolls or scroll air cooled at this point, they will have EXVs most of the time. I don't. When you factor just the efficiency side of it, there's not very many people that I'm aware of that are still trying to utilize TXV technology for these systems. Hopefully that answered your question. Kind of get off on a spill there on that one, but okay. Let's talk about the different types. So we've established that we're going to focus on the chiller side of this, and we get into these larger valve bodies. There's one important there's one important feature I do want to identify that we're going to talk about more as we get into some of the testing procedures. So right now we're just kind of laying the foundation, kind of giving some background and conversation around the EXVs, and we're going to get into how I go about testing these things in the field. One of the critical parts of that is a sight glass. All of these valve bodies will have a sight glass on them, especially these larger ones. I should say there are some smaller ones you'll get into on the tiny side that may not have a sight glass, but the vast majority of them they will have a sight glass installed. That glass is there so for testing of the valve. It is a very critical component. So I do want to point that out. So like in this example, you can see the sight glass pretty clearly here. On these, that sight glass is right here. And that's where that sight glass is going to be located. It's going to be right at the point of where we're going to see the valve sealing off. Now, this is done in a couple of ways. So I'll explain the other way that this can be done is instead of it being right here where you're physically seeing the plunger seat. So like you can see here, this is the plunger seat. So when you see this plunger move all the way down, you can physically see it seal. The other way that this has been done is the bottom of the plunger will have a stem, and the plunger may seat up here, but the sight glass will be down here. And so what we're looking for is where does that stem fall in the position. So if we see the stem is far up in the glass, the valve is open to some degree, and if the stem is down towards the bottom, then it's typically indication that the valve has closed. And that this is going to be critical when it comes time for calibration and doing our plunger testing and stuff. So I do just want to point out the side glass is a critical part of these valves and our ability to troubleshoot and test them effectively. Another thing we need to be aware of is the wiring. The majority of the valves that I see implemented in chillers today are typically a 4-wire valve. So here's this particular chiller has 4 different EXVs that it controls. All that's running through a stepper control valve. Now this is a separate controller from the main controller in this particular chiller. Some chillers, the valve itself will just come straight off of the main base control board, or you may have a subboard that just communicates back to the main board that controls these things. So you could have it either way. Just be aware of that. Um, but this this being a 4-wire, you can see we have a green, red, black, and white. This is your coils here. Now, in a 5-wire setup, what we would have is a 5th wire, obviously, but that 5th wire is actually a common wire. So when we have this 4-wire setup, we're going to trigger this red green is one coil, this black white is a second coil or second part of your stator. So your stator is split. These are stepper motors. Okay. So with the stepper motor, we energize one coil, we take one step. We energize the other coil, we take another step. And we're going to just continue to step through to open and close. Now, we change direction of rotation by changing polarity. And we can do that with these systems. So what that means is that when this motor, or when we're a positive polarity on the current and we're flowing positive through the green wire and then coming back out the red, we make rotate clockwise one step. And then positive through the black coming back on the white, we rotate positive one step. But if we swap the polarity where we send our positive through the red and we come back on the green, then we have now reversed the polarity. We've reversed the flow of the current through this stator, and we take a counterclockwise step. The same thing on the other set. And so that's how we can change from clockwise to counterclockwise. This would be a 4-wire setup. So these 2 wires are together, these are together. In a 5-wire setup, we have a common that comes back, and it'd be a 5th terminal here. And what makes these different is now all of these 4 leads tie back to that 5th common. And so we would give a positive current pulse through green, one step. Positive through red, step 2. Positive through black, step 3. Positive through white, step 4. And then we would just cycle back over again. Pulse, 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 pulse. And all of these are coming back to the main common feed on the 5th wire. If we want to reverse that, we would just reverse our polarity. And we would also step in a reverse direction. So we would go white, black, red, green, white, black, red, green. And we would step in a counterclockwise which would open the valve. So counterclockwise on these is opening. Clockwise would be a closing force. But yeah, all these would just tie back directly into that common leg. Hopefully that makes sense. But those are going to be the 2 main differences you're going to see between a 4 lead or a 5 lead for these valves. The vast majority of my C being used right now is 4 leads. Everything has moved that direction. At one point in time, it was pretty common to come across a 5 lead motor. Now, and I will say, from a electrical testing perspective, a lot of people, it's not that this doesn't work, okay? I'm not saying this doesn't work, but you have to be aware of how it works. They think that these are constant pulses to where you can just put your meter across these leads. So in this example here, we have a 4 lead, and if I just put my meter across these 2 leads, I'm just going to see my voltage, and that's not what actually happens. And this also depends on your meter and how fast its reaction time is for the reading. But if your meter is going to show a fluctuation, and which is really what you're looking for at that point, is do you see the pulsing when it goes to try to move the valve? What I mean by pulsing is your reading on your display is going to just flash back and forth from 0 to giving you a voltage, 0 to giving you a voltage, and it's going to do that continuously. And that is that pulsing action. That is every time that pulse happens on your meter, it's taking a step. Now, there are some meters who have algorithms built into their reading to help smooth that out. And so you may have some meters on the market that you'll take that reading and it may look stable on your meter. In reality, that's the meters just taking that pulsing signal and just giving you a consistent display. It's not what's actually happening at the valve level. So just be aware of that. Why some meters may give a pulsing, those are more of a live feed, and other meters may not pulse like that. It's because they're using a smoothing algorithm to level it out. You'll see this also in micron gauges. That's another classic example. With a micron gauge, some are a live feed, and that means that the reading on that gauge is the literal that instantaneous moment. That is the reading you have, while other gauges are uh, smoothed, meaning that it's taking a it's taking that reading in sections. So every so often it's averaging the total reading and then giving you something on the display. So it looks a lot smoother and more consistent, and it doesn't have some of the fluctuations. So that just comes back to the person. I personally appreciate a live feed, but you have to be careful with live feed because it can be more deceiving. Um, at the same time, having that consistency in the reading can make it easier to read and interpret, and we don't see so much fluctuation. And that's kind of the whole purpose of that smoothing, is there's not as much fluctuation to the reading, and it's meant to be more consistent and averaged. So just making you aware of that. When you're taking that reading, don't accidentally condemn a controller because you don't see voltage across those two pins the way you think you should. Chances are you may not even, your meter may not even be able to register that voltage, and it may do it just fine on one system and that style of controller, but you go to a different brand in this style of controller and it can't pick it up at all. That's just a difference in the manufacturers and how they're outputting that signal, what voltages they're using for that signal, and what how your meter is picking that up and interpreting it at the time. Uh, so yeah, 4 lead to 5 lead, taking those readings. That's the main differences between there. And to show that for, well, now we're going to get to that in our motor testing. Any questions up to just the different leads and how they're arranged? Come back over here, give you another shot of this. Like I said, this is going to be the most common style that you're going to start to see, at least in current times. Most everybody, Sportland and Danfoss both, on these scales of valves, they've moved to this 4-wire. I, I'm just speculating as to why I think that they've done that. I don't actually know the core reason, other than this is just what they're doing. Okay, so let's get into a calibration test. You see the valve body there. Come back up here. So one of the first and easiest tests to perform when we've got a valve that we're questioning. Now, there's lots of reasons to question a valve. If you're having superheat control issues, maybe you're losing superheat or you're running a high superheat, maybe your system's having a hard time maintaining the load. You could have something where the valve is occasionally tripping on a refrigerant loss alarm, a superheat issue, something along those lines. If you have a chiller that doesn't monitor suction superheat, it's probably monitoring discharge superheat. It will typically do one or the other, or sometimes both. And you may be having discharge superheat alarms as well. So it may not be just suction superheat. You may have a high or low discharge superheat. And if you're tripping on that, all of those, that could also be caused by a EXV issue. Or if you're having a liquid level sensor fault where you're not able to make liquid level set point in your evaporator if it's using that. A loss of charge, which typically you're going to see a high suction superheat or a high discharge superheat because you're running a low saturation. So most of the time, if you see a loss of charge, uh, a fault, then it's because your suction or your evaporator saturation got too low and it got down below freezing or got really low really fast, which would indicate that we don't have enough refrigerant in the system if everything was working properly. Now, that your first step in there should be we need to verify our valve operation. And just keep in mind, even if you have a new valve, these things fail, and it's okay. It's just part of the process. Um, I've had these valves last 1 to 2 months, and they just didn't hold up. There was actually a few. This is several years back at this point. Uh, the valves I was getting from York at the time. I did several valve repairs, and within a couple of months span, I ended up having to go back within 1 to 2 months of almost all of those jobs and warranty every one of those valves. And the only thing we could come up with was there was just a defect at the manufacturing level that didn't get caught. The valves made it just a little bit of runtime, a few weeks basically, and then they began to fail. They were typically failing mechanically, even though I think one of them may have been an electrical failure, but most of them were having a mechanical failure where uh, they were getting bound up, if memory serves. Pretty sure that was the case on those. Anyway, the point is, sometimes things happen, and it's just a defective component out the box, and you just can't control that. Either way, my point there is, uh, just because it's a brand new valve, don't just assume that everything is fine and that it's not having a problem. We always want to make sure that we're testing our calibrations for this. To do that, there's one especially easy way, but there's two ways to go about a calibration check. So the calibration procedure on these is fairly straightforward. These valves will first go through a closing calibration. What that means is that the controller will send a closing signal, or not say it'll rotate the stator to close the valve fully, and it will try to seat the valve. And this is where you get this loud ticking noise that you'll hear from valves sometimes. What that is that it's fully rotated closed. It's hit the dead stop of the valve body, and whether it be the threads or the clutch mechanism they have, whatever the case may be, it's the motor is still rotating where it's trying to, but it's skipping because it can't close any further. It has mechanically come to a stop. Now on the open, or the next steps, the first step is fully close. The second step is go to an open. So then it will initiate an open procedure. It will try to drive the valve to a fully open state. And you want to hear that dead head, or that stop point. So when you're listening for this, this is something that I'll put my hand on the valve, but I'll also be listening. And that's really what I want to do the most. I want to hear this process. I want to hear it fully seat if it wasn't already. Then I want to hear it come all the way back and hit the top end on the backside. And if I hear that, that's a good sign. If you're sitting there and you're listening and you don't hear this bottom or this top out, it's possible that the valve is whether it be sticking via the threads, or whether it have some bad threads in here and it's not uh, pulling the valve, the plunger back properly. It didn't make it all the way up to the top. Or even if it did, the threads are so messed up in here that it couldn't put enough force to bind the motor up. And I say bind in a positive way in this particular case. So if we don't hear that top out, that could be evidence of an issue. But the third and the final step to this calibration is it's going to go to a fully closed position. So we start off, we want to fully close. Then we're going to do an open stroke. We want to go full open. Then we're going to go to a fully closed stroke, and we're going to close again. Ideally, at each one of these points, we're going to completely come to a stop, and we're going to hear that valve ticking, right? So that'd be another way to describe it. It's going to have that tick that these will do. That is meaning that it's moved as far as it can go. That process can be initiated most of the time strictly by either power cycling the chiller. So if you fully shut the chiller down and then power it back up, most chillers have programmed in their software to automatically go through a valve calibration at the time of power up. On some chillers, you can do this by cycling the circuit. So every time a circuit is told to specifically turn on, and it's been given an enable command, before it will start the compressors, it will do a calibration on the valves if it's the first time it started up that day. Now, not all chillers will do that, so just be aware that it may only do the calibration at power up, and that's it. And then some chillers will have a manual calibration feature in the controls package. So you can initiate that, and they all do it in a variety of ways. So with some, you may have to manually input a position, and you tell it to go to 100% position and back to 0%. That'd be one way to do that calibration. Some control systems have a EXV calibration. It's not a button, but a feature to where you just enable it. And strictly by enabling the calibration function, it will cycle through that calibration on its own. So you could see this both ways. It just strictly depends on the manufacturer, and if you don't know how to use that feature, if you don't know how to get to it or the passwords or whatever, uh, while we have to be careful power cycling things, that is a backup default option. Just go and do a power cycle and let that control system just go through its normal boot up process, which will involve a calibration procedure almost all of the time. Yeah, I can't think of a machine that doesn't do that off the top of my head. Now, something to understand here. These valves in their makeup this is a threaded assembly in here. So, and these are typically made of Teflon. Now, the actual stem coming off of the motor may be a stainless steel or a steel shaft of some kind, but the actual threading piece that's attached to the plunger will typically be a Teflon thread. Why they go that path, I think it has to do with trying to prevent it getting in a bind. That Teflon will, even if something weird happens and the threads have an issue, that Teflon will kind of reform and shape itself in a way to where it can still be more reliable, more functional. Whereas if this was steel on steel, and let's say something got a burr or something weird happened, well, that steel is going to lock up, and these motors aren't that strong. So that steel gets in a bind, this motor may not be able to break it free. So your failure rate would probably go far higher than having that steel on with a Teflon thread. The other side of that is this is one of the biggest failure points that we see happen is this Teflon threading just wears out. And this ends up becoming what strips out. So a few things can happen that you can see via this calibration test, and this is where you get into kind of like a what I call a plunger test, if you will. So if this plunger cannot cycle all the way up and down smoothly, this valve will lose calibration. Uh, and it will do that because sometimes these threads, whether it be via like skipping a thread or a thread gets tough to turn past and it's got more resistance on it and it can't make that revolution the way that it needed to, then it can basically like skip a beat, if you will, and the motor has to try to put enough torque behind it to get it past that tight spot. These valves are designed off of a timed uh, cycle, very similar to an actuator. A lot of, say, floating point actuators are based off of time. And so they could be either a 60-second, a 30-second, a 90-second actuator, right? And so we know that in that time, that actuator takes 90 seconds to go from 0 degrees of rotation to 90 degrees of rotation. That's very normal actuator terminology. Well, EXVs have that exact same process. You have a 30-second valve, a 60-second valve, something along those lines. So there's no feedback to the control system from the valve to tell the controller, I'm in this position. So when you see that feedback on the display and it says that it's at 80% valve position, that is a estimation. That means that if the valve worked like it was supposed to and it was properly calibrated, it would be at 80%. But in some cases, as that valve begins to wear down, uh, and it doesn't move like it was intended to, it may be at 50%, but the controller thinks it's at 80%. And then when that controller reaches 100%, but that valve only made it to 60%, the controller thinks it's at full open. And that is not true. And that is a very consistent failure that you will come across with valves like this. And that's part of what we're testing for when we do a calibration test is how does the valve move? How does it sound when it moves? So this is where using your sight glass and using um, uh, your listening come into play. And having a mechanical failure like this is one of the more common failures that I personally have dealt with. There are electrical failures, and we'll look at that. This one in my hand failed electrically, but mechanical is the main failure that I personally have dealt with. So with that calibration, if the motor can rotate at all and that valve is changing position at all, chances are your stator is okay. That's not your main issue. Then if the motor itself is not the issue, then we have to start looking at the mechanical aspects. And in that calibration process, did the valve hit its end stops? Was it even able to move far enough to do that? And that's one of the I alluded to this earlier. That's one of the ways that I've caught mechanical failures like this before. You'll get that open pulse especially. So let's say it was able to make fully closed, but then you'll get that pulse open. And let's say this was a 60-second valve. Well, in a calibration, from what I've seen, most controllers will go a little bit more than the valve's rated time. So if it was a 60-second valve, it may do the opening process for 65 or 70 seconds, something like that, because it's calibrating, right? So we want to make sure that it can intentionally hit the full top end. So going from fully closed to open, there should always be, if everything worked right, there should always be a little bit of a stop for just a moment, even if it's just a couple of seconds, where you feel and you can hear that valve hit the top end. And when that doesn't happen, and you can see in the plunger or through the sight glass that the plunger didn't move, in many cases, like it will move to the point where you may not even be able to see it in the top of the sight glass anymore. Like it's out of visible range. Or you may just barely see the very bottom tip of it. Uh, but that didn't happen. So you go through that process and you can still visibly see quite a bit of that plunger sitting in the sight glass. And then it goes back into a closed calibration. That right there immediately indicates to me that my threads are not functioning properly. And I'm not actually getting my full stroke on my valve, which means that I'm likely to starve my valve because it's able to close better than it can open. And then you apply refrigerant flow and refrigerant force through there, which most of the time the refrigerant's going to be coming against the valve piston to where we're pushing down on it, making it want to open less, right? Most of these valves, that's how the cycle goes through them. You can see that here in this process. We're coming through, the valve is trying to open up, but our refrigerant force is pushing down on it. So if we're at a standing state, we're not even running or flowing refrigerant, but we can't even open the valve at that state, how much worse is that condition going to be when we start flowing refrigerant? You can also see that here. We're closing in a downward position, flowing out to the right side here, but we're coming in and flowing down. So when this is trying to open to increase flow, we have the same threading mechanism here that we do over here. Okay, this valve is the same basic concept, just in a different orientation and a slightly different plunger. So the plunger is different here, but the flow process is all the same. This is one of the tests that can sometimes get you tripped up at times because in some cases you may get that valve to fully stroke with no flow. But the moment there is flow and there's force acting against that valve, it can no longer, the threads are too weak to continue opening and getting an increasing flow for that refrigerant. So that's one of the things we have to be careful with. Doing a static with it off test does not mean that we are fully uh, functioning properly for sure mechanically. But there's another symptom that comes alongside this when we start getting to that stage. So when our threads start to get wore down, they start to typically bind a lot because they're not making a proper fit for the threading and um, the shaft coming off the motor. And so because we don't have a good fit there, they'll get in a bind frequently. And you can hear that. So for an EXV, if you have a lot of noise from that valve and it's just making this really loud ticking sound the whole time it's trying to cycle, doesn't matter what position it's in, that is evidence of a mechanical issue on that threading. A new TXV where everything's properly done, it may be silent and you may not even be able to feel it, but it will likely be silent throughout its in-between travel. And you'll only hear it bottom out and top out, and that's it. And even the bottoming and top out side might be fairly quiet. Not always, so it just kind of depends. But if you can hear that same ticking noise in during the travel in between that top and bottom, that valve is likely, if it hadn't fully failed yet, it's probably not that far from it. So these are things to be aware of and to be paying attention to in the process of all this, making sure that we're listening and we're monitoring through our sight glass and that we are getting a proper calibration. Um, they make testers out there to do this where you don't have to do it through the control system. They're worth investing in for sure. I personally haven't. I've always just done it through my controls, and I've been fine up to this point. Like, it wasn't a tool that I had to buy, but I will say that I can acknowledge that it would be a very useful tool and it would be very resourceful to have that on site if you have a tool that can cycle that valve without having to go through the chiller's control package, especially when you're in a situation where you're trying to determine, is this a valve issue or is this a controller issue? Because the controllers fail too. I just find that they don't fail near as often as the valves do. That most of the controllers we have in the market so far seem to be pretty robust overall. So yes, calibration, plunger test. We're listening for the noise. We want to get the top and bottom out sounds, and we want to see how that's moving through there. We also need to be aware that we may pass a calibration, but they may only last for a certain period of time. So this is real common where um, you'll get the alarm, you'll clear the alarm, it'll go through a calibration on the valve to turn it back on, and then it will run like that for most of the day. And it won't be till sometime late that day or that evening before it trips back out again. That's a typical symptom. And what that means is that that valve is mechanically in an early stage of failure, and that its position is not controlling correctly, um, as it is able to operate. And as the refrigerant force and everything else that's happening against it, it's losing that calibration. And so, even though the machine thinks it's at 100% valve position, it's really only at 50%. And it just doesn't have any other way to know that. Anyway, any questions on that part? And then I'm going to cover the motor testing and doing some repairs, or how I go about that process. But any questions so far? All right, awesome. So, motor test. The motor test is fairly simple for most of these. With this, it is quite literally as simple as you get your leads. Now, whether this is pulling them off the terminal block, whether you have a plug here, either way, for a 4-wire, 2 wires go together for each coil, for each stator. And so, reading resistance between these two, I will get resistance. Between these two, I will have resistance. So this particular valve is like a 50 ohm valve. This could fluctuate a little bit depending on the manufacturer, the size of the valve. So this changes. There's not just one standard for this. But just to kind of paint the picture. Now, that also means that in a 4-wire, these other two coils don't intersect at all. So between the red and green coil and the black and white coil, there will be no uh, there will be no electrical connection between there. I have to be careful with how I term that, but they're not connected electrically, and there's nothing connected to ground either. So the failures that can happen, and like this particular case, this black and white has 50 ohms across, but the red to green has OL. Nothing to ground, none of these wires to ground, and there's no internal short. So red and green to black or white, nothing is connected there. But the stator failed and on the red and green winding. Now, in the event that this was a 5-wire, we're just checking basic ohms here, and I'm not saying continuity, I mean ohms. Okay. Hopefully, most of us are familiar with that, but continuity is that's just stating that your ohm value is less than a certain amount. So most meters will show continuity if it's less than, say, 20 to 50 ohms. But the moment your ohm value gets above that, it won't beep continuity anymore, even though you may still have connection. So if you've got a coil that's running 80 ohms on the coil, you're not going to show continuity, even though it may be from an ohms perspective properly connected. Just be aware of that. So please don't rely on continuity for a test like this. That is not correct. Anyway, in a 5 wire example, our 5th wire would be what we would hold as one test pin or test point, and then we would go to each of our other 4 wires. And so we'd have, say, our a blue 5th wire. So one lead would go on the blue, and then we would take the other lead and test to each of these others. And they should all have the same ohm value. And even between this 4 wire, the two stator coils will have the same ohm value. These would have 50 ohms across both of them. Uh, if this one was good. In the same way on the 5 wire, each of those are going to have the same ohm value. So if it was 20 ohms between each coil, then you want to see that. And if you have one that doesn't have that, that would be an indicator of a failure. So that's one reason why I say just strictly continuity is not good enough. So you could have it to where the it should be 20 ohms, but one of those on a 5 wire example, or even on these 4 wires, I've had this happen before where one coil showed 50 ohms, the other one showed 30 negative. That valve had an electrical failure. Something shorted in the stator, right? Depending on your meter, both of those could have shown continuity. In a 5 wire example, if they're all supposed to be 20 ohms across the different state or coils, but one of them has 5 ohms, again, you're going to show continuity, but they're not correct. So I'm really stressing that because a lot of technicians I've worked with really don't grasp the continuity concept versus just taking an ohm value. So please, like, pay attention to your ohms. I don't care about continuity at this point. And then check all that to grounds. 5 wires are not going to have anything to ground either, so nothing should be grounded. And you can do that just by testing to the valve body itself. So by just reading from your leads to the copper line set to the valve body, whatever you've got close to you, or if you're doing this from the control cabinet and you're testing at the end of the harness, then just test that to a ground point inside of the cabinet. That works just fine too. Just if you find one that has bad values, you've just got a bad motor. It's going to lead to replacement. And these valves are not meant to do a motor replacement. So while technically from here up is your motor and here down is just strictly mechanical part of the plunger, you're not going to separate these and replace that. That's not going to go well. If you're going to replace this, you're going to replace just the whole head assembly itself. Don't try to. I know with smaller valves, there are some on the market that you can do just the motor on. Those ones you see on mini splits, as an example, the coil, the stator is meant to slide off. It's just a ring that sits over it. That's not true for these larger valves. Electrical, mechanical failure, either way, that head is done. The body itself may be fine, but the head is done. Um, I talked about earlier, trying to take an electrical voltage reading. That is a method of trying to verify if you're getting uh, um, power to the valve in pulsing, but you have to be just very careful with that. Now, one of the other things that you need to be mindful of, if you do a repair and you replace one of these valve heads, making sure that the polarity is correct. So these, as an example, I've had it to where the polarity changed from an older style to the newer style, or even just from valve to valve. Sometimes like it's exact like for like swap, they're identical, but one rotates in a different polarity. So when we're doing a calibration upon replacement and stuff, make sure that you're actually paying attention. And when it's supposed to have a closed call, it actually closes. And that's again where the sight glass comes in. You can see that process happen. If it doesn't close, if it does reverse, and when it's supposed to be closing, it's actually opening, and vice versa, let's just swap the wires. You just swap the wires of where it wires into the harness. That will reverse the polarity, and it will sync everything up. Okay, so it is a very simple fix, but it's something we have to verify upon repair. Otherwise, we're not going to have control of our valve, and we're literally doing the opposite of what we needed to do at the time. So this is something to just be aware of, and it's part of the commissioning process for an EXV. Make sure your polarity is the same. Doesn't matter if it's like for like or not. Always verify the closure and opening a direction, and that you have correct polarity. And every valve that I'm aware of on the market, or every controls package, will do that 3-step process: fully closed, fully open, fully closed. That is considered calibrated. Uh, any we're coming close on time here. Any other questions on the motor side before I get into how I go through a repair process? Okay, so repair on these for me is fairly straightforward. So what I'm going to do is my go-to is just replace the head. And these, while there are if you have some really big crescent wrenches, you might get them to fit on a lot of these larger valve bodies. They're not going to fit. They may fit just fine on the smaller ones. So if I can't make my crescent fit, then I will get my pipe wrenches out. But you have to be very careful because pipe wrenches will dig in, and if you're not careful, you can actually end up tearing this up or warping the bodies and such. But these are in there with a lot of torque, so that's one of the things you need to be aware of. These have to be torqued in order to get this seal to function. I do personally believe in using a little nylog on this. I do think that helps. There's a lot of technicians out there who disagree with that and think that just keep the metal to metal pure. Um, I think it just comes down to preference at that point. Personally, I don't think one way is truly right versus wrong. It's just what are you comfortable with and what practices are you used to doing. Now, um, with that, just make sure you're just being careful with what tools you're using trying to do this. And the way I will go about bidding one of these is the majority of the time the body is not the problem, it's the head itself. And so I don't need to change the body out because that's a tremendous amount of extra work versus just doing a head swap. But I can typically bid it two ways. Um, because my labor and my material is far less if I just do a head swap, I'll usually build an optional thing and I'll communicate this with the customer and say, hey, listen, I want to do a head swap, but in case there's an issue with the body, I may have to do a full body change. And when you buy these valves, you're gonna have to buy the whole body most of the time. It's pretty rare that you're gonna be able to purchase just the head assembly itself. Okay, so just be aware of that going into this. There are some that will do that, but most of the time you're gonna have to get the entire body with the head. So what I will do, option one would is we'd go in and we pull the head, we do an inspection, and as long as there's nothing wrong with the original body, we just pull the new body or the new head out of the body it came in, and we just do a head swap. Now, if that's all that it was, and we do the head swap and everything's good to go, then it's a very simple job. We're done. But I will put in there a secondary option to where if we discover that there is an issue with the body itself, then this amount extra will have to be added to the total invoice so that we can then change the body and go through that whole process, which depending on your chiller and its setup and the size of everything, it could be a pretty difficult process to get that body sweated out, sweated back in. Which is why I'm not a fan of going that direction. It is my personal opinion and my personal experience that very rarely did I ever have to change a body out, and it was almost always strictly a head problem. So Yeah, it was very rare that the body had something wrong with it. So that's why I just encourage you to have that as an option. That is a way of still CYA. You know, you still have it. They've agreed to doing the body process, but if you can save them time and budget by doing just a head swap, which saves you a lot of headache, then that's great. My personal opinion, whether I'm changing the body or not, I'm gonna pull that head out of the body. I don't want to leave that in there while I'm trying to sweat and risk that it getting messed up. One, the Teflon threads. Two, these will have rubber seals and such that this is what's sealing against the body to stop the refrigerant flow. So those things don't take heat very well. And especially with the size of these valves, we have to get the bodies really freaking hot in the piping in order to get uh, the brazing. T- um, Gee whiz, getting stumbled on my word. Not solder. To get the brazing rod where it needs to go. Right. It takes a lot of heat at this size. I mean, we're talking inches in some of these valves. So I'm not a fan of trying to sweat that, especially with the head in the body or even the sight glass. I am personally, even if I'm going to do the whole body, I'm going to take it all out, sweat it in where I don't have to have the same tempering control. I'm not going to mess it up. And then I will reassemble it after it's had a chance to cool back down. That really helps simplify the whole process. You're not trying to fight this large pipe size right next to a bunch of wet rags, trying to keep everything cold. And my personal failure rates of uh, whether it be leaks or damage to the actual head assembly just completely disappeared when I went this path. So that's my personal process and preference. If I am going to sweat it, that's how I'm going to do it. If I can do just the head, which most of the times I can, I'm going to do just the head assembly and call it good from there. Um, It is also important to note that these plungers can extend further than most of the valve bodies are actually need them to. So I've had apprentices do this before where they wanted to see the valve work, so they hook it up and they test it before they ever put it in, which isn't a bad idea. But one of the mistakes is part of the calibration. We stopped the test at fully closed. Two things can have happened. One, the valve has extended past the threading, and so then it comes off the threads and it won't retract again. So whenever they try to tell it to retract the plunger, it won't. It's stuck in an out position. Well, that's because it went past the threading. If you just put some pressure on it, push it back in, then initiate the test, those threads can regrab and it will thread back in just fine. The other thing is they'll do that and then they'll forget to draw it back in, and the plunger will be out at an extended position, and then they'll thread that in, and it'll go majority of the way, and then you'll think that you're close enough. You just need to finish torquing it down. In reality, you hadn't actually bottomed out yet, and what bottomed out was the plunger to the valve body, not the actual sealing surface. So then you go to start torquing it down, and you'll end up jamming that Teflon thread assembly and just stripping it completely out. So that's another one of the a common mistake when doing a body change like that, or a head change, is if you're going to test this or do any kind of calibration checks before you put it in, make sure that it's in the fully open position before installing it into the body. If you have it at a fully extended, um, you will end up bottoming it out trying to thread it in, and then you will end up tearing the threads up because it went too far. And this valve will extend that plunger further than the body has depth to go. Very easy, but very common mistake that I have seen happen. So yeah, that's my personal take and preference and how I go about things with a EXV testing, troubleshooting, repair, whether we're doing mechanical tests and a electrical test on the motor. or just doing a repair on the valve itself. Any final questions? If not, I need to conclude this, and we're at our time here. I've got another class coming up after this one. Any other final questions? All right. Well, with that, I really appreciate your time. Hope you got some good stuff out of this. The recording for this will be sent out on Monday, and I hope you all have a good day.